This video covers the topics of the center of gravity and the centroid for an object. When we're talking about a rigid body, say it looks like this, it's really made up of lots of individual particles that are all rigidly bound together. And each of these particles has mass, and so gravity is acting on each of these particles. So there is a force, the weight of each particle, acting at each point, like this. And so if we want to describe how the weight of the entire rigid body acts, then we just consider the integral. So the weight of the entire body is the integral over the entire area of all the smaller weights. And so in the manner that we learned from previous topics, when we have a system of multiple forces, we can simplify it into an equivalent force. So here this is supposed to be the same body as that. Then we can take all these smaller forces and talk about an equivalent force, and that will have magnitude of weight, which is given here. So it's the summation of all these infinitesimal weights, or the integral over the entire volume. And now if we want to find out where it acts, a point on the line of action of this force, we'll call that x bar, or x tilde, y tilde, and z tilde, and we call that point G. Then we will look in the same way that we did when we had distributed loadings and we wanted to find, so say we had these two forces and they were at x1 and x2, and we wanted to describe an equivalent system where we just had one force and I was acting at x bar. Then the way we found out the location for this, assuming this magnitude was equal to the sum of these magnitudes, was that both of these systems have to generate the same moment about any point. So we could pick this point here at the end, and these two forces generate a given moment about this point, and this force has to generate the same moment about this point. So since the magnitude is fixed, then that gives us this distance x. So that's how we'll find the location of G, because the moments generated by all these infinitesimal weights has to be the same as the moment generated by this one weight acting through point G. So you see in the figure on the right that each dw, each small weight, is going to generate a moment about x. So if we take the integral of all those weights, then we can use that to get the location of G, or x tilde. I'm sorry, x bar is what we'll call. So x bar is the location of the centroid. X tilde is the location of each infinitesimal weight, or each particle. So that equation is x bar times w. So that's the moment from that the weight generates about the y-axis. So the weight will be acting through point x bar, and so it'll generate a moment about the y-axis. And that has to be equal to the integral of x tilde dw. So that's equal to the summation of all these infinitesimal weights and the moments that they generate. So that's the general idea of how we can come up with equations for locating the center of gravity, x tilde dw divided by w, which is integral of dw. So that's how we locate the center of mass. I'm sorry, that's how we locate the center of gravity, where the force acts. And then for the center of mass, if we want to find out the average location of all the mass, then we can use the relationship for an infinitesimal particle. Its weight is given by gravitational acceleration times the mass of that particle. And so that's assuming, if we assume there's constant gravity acting over the entire body, which is close enough to true, then we can get that the center of gravity, or I'm sorry, the center of mass is located at the ratio of these integrals. And then finally we have the centroid, which is the average volume, the location of the average volume. So that's the centroid. We've talked already about centroids for an area, and now we're just talking about centroid for a 3D body. Like for a rectangle, the centroid is in the middle, halfway up and halfway over. And for a right triangle, it's 2/3 of the way and 2/3 of the way, or 1/3. So those are the centroids for these planar shapes. And to get the centroid for a rigid body, then we assume that, or we use this relationship, so the mass of that particle is given by the density times the volume of the particle. And so assuming that we have constant density over the entire body, then we just say that this is the location for the x-coordinate of the centroid. So one point about the centroid, or center of gravity or center of mass, is that it, assuming, you know, constant density and constant gravity, then the centroid is going to lie, well, first of all, centroid, center of mass, and center of gravity are all at the same point, same location, assuming we have constant gravity or gravitational acceleration and constant density. And if there are any planes of symmetry, then the centroid will lie on that plane. So here's a shape, it's a cone, and it has two planes of symmetry. It's symmetrical about the xy plane, and it's symmetrical about the yz plane. So that means that the centroid is on both of those planes, and points that are on both of those planes are basically the intersection of those planes, which is the y-axis. So we see from that that the centroid has to be somewhere on the y-axis, because it's on the xy plane and it's also on the yz plane. We'll often want to find a centroid of an area whenever we're dealing with mechanics. And so here's an area, and we want to find the location of its centroid, x bar and y bar. And we can use this equation. So the integral over the entire area of x tilde dA. So this is the location of the small area, so x tilde. And then dA is the area of this, so it's dx times y. So in this example, we're just using a single integration. And then we want to divide this by the total area. And so what this is really giving us for x bar is a weighted average, because we're integrating x tilde over the area, and then we're dividing it by the area. But it's really a weighted average because we multiply each value x tilde by dA, and over here x tilde will have a larger dA associated with it because the rectangle will be bigger, and so that value for x tilde will be multiplied by a higher number than, say, this value for x tilde. X tilde over here will be multiplied by a smaller dA, and then we divide that all by the total area, and so we get a weighted average. So that means that the centroid, the x value of the centroid, is going to be closer to the left side. And so that's for an area, and then we can also look at a line. So in real life, if we have a wire or a rod, something thin, then we can treat that as a line segment. And we can find the centroid through integration here also. And this figure shows another concept, is that the centroid is not always on the body. So for example, if we have a ring, then the centroid would be located in space in the middle of the ring. So here's an example. And we have this area, and it's bounded by the x-axis, x equals 1, and then this curve y equals x squared. And we want to find the location of the centroid, x bar and y bar. So all of this material is intended to give you an understanding of the concept of a centroid. It's not so important that you be able to, exactly replicate this part. It's really just important that you get a handle on what the centroid means, and then also what the center of mass and center of gravity means. So here we have this shape, and we're going to do a single integration. So we'll integrate from x equals 0 to x equals 1, and we'll find x bar is equal to integral x tilde dA divided by integral of dA. We're integrating over the entire area. So here we have dA is the area of that little bar, that gray shaded space, and that's equal to y times dx. And x tilde is equal to x, whatever x value we're integrating over. So we'll just find the x location for the centroid, because the y location is the same thing, or really similar. And then here we'll substitute y, so y is equal to x squared from the equation for that line that defines the upper limit of that rectangle, the gray rectangle. So the integral of dA over the area is from 0 to 1 y dx, so that's dA, but then that's 0 to 1 of x squared dx, which is one-third. And then the integral x tilde dA is 0 to 1 x times dA, which is y dx. So and using this equation at the top, then we get x bar is 1/4 divided by 1/3. So it's 0.75. So you can see that it's 3/4 of the way over here, which makes sense because the x tilde is going to get multiplied by a higher value over here. It's going to be weighted towards this side. So conceptually, that's how we find the integral, but in practice we're typically working with simple shapes in engineering, especially for structural engineering, where we're constructing things out of I-beams or angle iron or tubing. And so in that case we will be looking at composite bodies made up of simple shapes. So Okay. So whenever we want to find the centroid for a composite shape like this, it's the same concept as before, where we were dealing with infinitesimal particles. So, before we found the area of, or the volume of this place, and we integrated that over the entire surface. So it was the centroid of all these tiny little pieces. And what we have now is it's the same concept as the centroid, or using infinitesimal parts, but now instead of an infinite number of these little pieces, we just have a few parts, a few bigger parts. And so we're going to have summations instead of integrals. So for example, the x location is, and this is for the center of gravity, x tilde times weight, the sum of all the x tilde and weights divided by the sum of the weights, where x tilde is the centroid of the part, and w is the weight of that part. And sometimes, or oftentimes, we'll have shapes where they have a hole in them. And so let me see if I can find this figure. Okay, so here is a cone with a cutout in the bottom. And the way we treat that in this equation is that the cutout would have, would have a negative value. So in this summation we would have x tilde, or really x tilde 0. So we'd have z tilde and w for the cone, and then minus z tilde and w for the cylinder cutout. So what I'm saying is that holes have so in these summations, if we have any holes in the composite piece, then those holes are in the summation but as negative values. So, some examples. First, we'll start out with fundamental problem number 9. Number 8. When we do these problems, it's helpful to make a little table for when we're working with composite pieces. So we'll have a table with the data for each component. So this composite body we're going to treat as being made up of 2 components, or 2 segments. So we'll call this segment 1, call this segment 2. And first of all, what is the x coordinate for the location of the centroid? Well, you should see that there is a plane of symmetry, the YZ plane, or it's symmetric about on either side of the y-axis if we're looking just in 2D. So the centroid is on the y-axis, so x bar is 0. And now we want to find y bar. And so we'll use this equation. Y bar is equal to the quotient of summation of y tilde times a divided by the sum of areas. So here's the little table I talked about. We have segments, and then we have the centroid for each segment, and then we have each segment. So segment 1 and 2. It's really simple for this piece, but when you get to more complex parts, then it's helpful. So segment 1, its centroid is located at y tilde is 325. So 300 plus half of this distance, so it's 25. So 325 is right here. And the area of that is 50 times 300. So well, we'll go ahead and skip a step. So y tilde times a. So we have y tilde is 325, and then times a is 50 times 300. And that is 4.875 times 10 to the 6 millimeters cubed. And the second segment has y tilde of 150, and its area is the same, 300 times 50. So y tilde times a for that is 150 times 50 times 300, and that is 2.25 times 10 to the 6 millimeters cubed. So y bar, the location of the centroid for this composite shape, is 4.875 plus 2.25 times 10 to the 6 divided by 2 times 50 times 300. 2 times 50 times 300 is the areas of the two added up. 50 times 300 for two parts. And so that gives you that y bar is 237.5 millimeters. So if that makes sense, you'd want it that it's higher than halfway up this section 1. Now we'll go ahead and do another example, and this is problem 78. So here we have a composite body that's made up of, we'll consider it to be 2 segments. Segment A and segment B. And in this case, we need to find we're going to find the Cartesian coordinates for the centroid, x bar, y bar, and z bar. So then we're going to have to get the centroid for each segment. So x tilde, y tilde, z tilde. And in the previous problem we were finding the center of gravity. In this problem we're finding the centroid. They're only different if the composite body is not made up of the same material throughout. So if it's homogeneous material, then the center of gravity will be at the centroid. And so we need the volume for each part. So segment A, segment B. So for segment A, the x-coordinate is 1. The y-coordinate for its centroid is 3. Oh wait, I'm sorry, that's for B. Okay. X-coordinate for A. we go out 2, and then we go another 2, so that's 4. And then the y coordinate now is just half of the width, so 1. And z is 2/3 of the way up this right triangle, so it's 6 inches high, so 2. And the volume is just the area of the triangle times the thickness, so 1/2 6 times 6, and then the thickness is 2, so that's 36. That's cubic inches. And then for component B, x tilde is 1, y tilde is 3, and z tilde is 3. And the volume is, the volume is 1 times 3 times 3, so 9. Oh, the volume, I'm sorry, I was too quick. The volume is 2 times 6 times 6. So it's 72 inches cubed. So we'll just use, for example, x bar is sum of x tilde times v divided by sum of the v. And so that is 4 times 36 plus 1 times 72 divided by 36 plus 72. And that's 1.47. Y bar, again, this is sort of a weighted average. So we're averaging the centroid of these two bodies, but we're weighting those centroid locations by the volume of each body. So the centroid for the composite body is going to be closer to the centroid of B than it is to the centroid of A. So I might have, and I hope not, acted too quickly here, because, okay, so we're finding in this problem, sorry for the mistake, we're finding in this problem the location of the center of gravity, because this is an example where the parts of the composite body are made up of different materials. So part B is denser than part A. So not only is it larger, but it's denser also. So we need to find the location of the center of gravity. So the center, so that looks like for A we have 4, and then weight is specific weight times the volume. So we have 4 is x tilde, and then for body A, the specific weight is 150 pounds per foot cubed. And the volume is 36 inches cubed, and then we need to multiply that by 1/12 feet per inches cubed to convert the units. And then the sum of the weights is just going to be, well, that was, okay, so this was the weight for part A. Okay. I really wish I could just go back and delete the last couple minutes, but I should have had another column in my table. So let me just get the weight of A. So the weight of A is this 150 times 36 times 1 over 12 cubed. And that is 3.125 pounds. And the weight of B is, its specific gravity is 400 pounds per cubic foot times 72 cubic inches times 1 over 12 cubed. And that is 16.667. Okay, so x bar, again, now we have 4 times 3.125 plus 1 times 16.667. So we have x tilde times x tilde A times weight of A plus x tilde B times weight of B divided by weight of A plus weight of B. And that's 1.47 inches. Y bar is 1 times 3.125 plus 3 times 16.667 divided by, and then this is the sum of the total weight of the object, weight of A plus weight of B, 19.792, that's 2.68 inches. So we get that x tilde is 1.5 inches, and this, or 1.5 inches. Y tilde is 2.5 inches, and z tilde is about 2.5 inches. So the centroid is somewhere about there. Sorry for that mix-up. So now we will look at one more problem, and this is a problem where our composite body has a hole in it. So this is number 83. So we want to find the distance z bar to the centroid, where we have this cone with a hole where h is 50 millimeters. So the centroid means we don't have to worry about density because we're just concerned with the volume. So this is going to be not a very good drawing. We'll call the cone segment 1 and the cylinder inside the hole is segment 2. So here's our little table. Segment z tilde, so the z coordinate for the centroid of the segment, and then the volume of the segment. So segment 1, segment 2, z1 is, so for a cone, and this is where we refer to the back cover, or the inside of the back cover of the book. It has equations for these 3D shapes. So here we see that for a cone, the centroid is located at h over 4, and so in this case that's 500 over 4. This is in millimeters. It's millimeters cubed. Z2 for a cylinder, the centroid is just half the height, so that's 25. And then the volume of a cone is 1/3 pi r squared times h. and that volume is 11.781 times 10 to the 6th. And the volume for a cylinder is pi r squared times h. So pi times 50 squared times 50, and that is 392,699. So Z bar is 125 times 11.781 times 10 to the 6th plus 25 times 392,699, and that's divided by the sum of the volumes. Z bar is 122 millimeters. So, I made another mistake. Can you guess what the mistake is? So, we have here a hole, and I forgot to treat it like a hole. So actually, these should have been subtractions instead of additions. So, segment 2 is a hole, so we're going to subtract that from the summation. So Z bar is the summation of Z tilde V divided by the summation of V. So when we're doing these summations, when we have holes, we're going to subtract. So it's a negative value. So this should be minus. That should be minus. So let me recalculate. So that's actually 128 millimeters. So you can see removing this material moved the centroid up a little bit when I thought, from where I thought it was, or where I originally calculated. So that's one thing that's easy to do, is to make the table, but then forget when you're doing the summation that holes are actually negative values. So that's one thing to watch out for. And then the other thing to watch out for is just making sure that whether or not you're looking for the center of mass, center of gravity, or you're just looking for the centroid. The first two depend on the density of the materials, and the second is just the volume. So if you have heterogeneous materials and you want to find the center of mass, then that's going to be a different location than the centroid. So center of mass, you have to be concerned with the density of each component.